there are a few parts. I hope I was planning for like 35 minutes. We'll see how it will happen. I will start with this kind of argument against counting measure in many words, which for me it's very strange. There are some people who look like very clever people believe in this strange thing, and maybe it will give kind of one of the argument how I'm going to prove the Born rule. And then in the middle I will kind of sneak my view of many words and my view of wave function, and I will give kind of a proof, but if do it very carefully, probably will take much longer. I will not try to do it very carefully, but I will, yes. The idea is that it will kind of allows, I think, to ask questions. Well, we need to start with something, and then we can, maybe I will get some answers. Maybe some of them I have, some of them I'm not sure, some of them I really don't know. So I think there are many questions about Born rule. The first, even if do we really need the proof? There are many people who are trying to do this, and for a long time, for me, and even now, I say, okay, we have this. Every quantum mechanics has this postulate. Not many words, every postulate. So many words also has this postulate. Well, why do we need the proof? And I'm not absolute. I'm not sure that the many words help. There is. So this is really maybe the third question. If in the framework of many words it's easier to prove Born rule rather than not in a collapse theory, it's not clear for me. I think at least my symmetry proof works in both cases. And I'm not sure that we need it because my feeling is that we need to assume. We cannot really prove it from nothing. We have to make some assumption. And if we have to make some assumption, why not to assume the rule itself? But still, if we're in a game, what kind of assumption we need? What is the minimal assumption? Now, there are many proofs. Now I present one of them. I'm trying to be familiar with other proofs, but I'm not sure I fully understand. And some people here made the proof so that they can say if it's the same or it's different, or maybe what I did it wrong. So this is number 5, if there are some holes in my proof. One of the things which I kind of using, and I'm not trying to derive, maybe I can go forward, I use density metrics. And I wasn't aware so much, but I asked people who say that there is a problem with it, and now I appreciate that there is a problem with it. That for me, density metrics was part of the formalism. I remember in Landau-Lifshitz, the chapter 14, which is one of the beginning, density metrics. But then it says it's complete description. Now, and the fact that it's complete description really, in a sense, relies on the probability rule. So if we require that it's complete description, it's kind of important for the proofs. But for me, it's part of the formalism. Can we assume it, or we're not supposed to assume it? Can we derive it? Because my feeling is that we don't assume it, then we're kind of pretty lost. When I have entangled system, how I describe one of the system, it's not clear for me what exactly it means. It also means that I'm not sure what. I'm not sure it's here. What is quantum measurement? Quantum measurement is also part of the story. I think it has to be very well defined, and the Born rule, and without specifying what exact procedure which called measurement, it's. I think it's hard to see. Okay, maybe some other. And okay, let's try to do. The first is naive approach to probability in quantum mechanics. The probability given by the number of words, and many people dismiss many words because this is not what we see in experiment. So I consider the basic experiment piece of glass that most of light goes through, and but 10% goes reflected. And then I would bet if I send a single photon 9 to 1. But if there are two words, then some people say, okay, the probability should be 50-50. There are two of them. For me, it's very strange approach, but let me see how I can kind of kill it. I think one thing which I can assume is that physics, which I know, and I think special relativity is something which I really believe. So I think using special relativity, this assumption can be, this number of words probability can be refuted. So I consider the same glass, but now I put many more glasses, special glasses, such that here it's 10%, but I arrange that it will be, again, 10% of everything, so it should be some different glasses in a sense. So I put these all glasses so that the amplitudes and all 10 detectors will be the same. So in this case, the people say the number of words, the probability is going according to the number. They should say that everyone should have 1/10, because now there are 10. We have 10 detectors. I also arrange it that every detector has the same amplitude, and at least in this case, I think it's reasonable to say that they have the same amplitude. So there's more reason to say. But anyway, the people who believe in the number of word hypothesis doesn't matter what is the amplitude. There are 10 words. The single photon can be detected only by one detector. So the probability will be 0.1 in everyone, in particular here. Before, it was, in this case, 0.5 in B, because it's the number of words. But now, in this kind of situation, it should be 0.1. So I can arrange the following. I can put these detectors far away, and if I don't put any kind of another beam splitters here, and the assumption, the probability going according to the number of words, there are only two words. It's either here or here. So probability in B is 0.5. All this area might be in space-like separated region. I can add here many detectors. And now to answer that some other idea with splitting of words, that maybe it's happened every event. Now I can arrange that photons arrive at the same time to these 9 detectors. So it's essentially 10 words, because we have a possible 9 detection or 1 non-detection, and this is a 10th word. So if I put all these beam splitters here, then probability here should be 0.1. And if I don't put, it should be 0.5. So I can send signals from this area to this area, and I don't believe this kind. So this hypothesis contradicts special relativity, so let's forget about it. But I forget it all from the beginning. I think it's extremely strange. Why? There is no symmetry here. Why would I put the same weight here and here? Because they are different words. This is word A, this is word B, but they are different. And especially there are some numbers here different. I see no reason whatsoever to start with it. I want to now use symmetry. I think if we have symmetry, we do have reason.
Is it okay to interrupt?
Yes.
Are we into this?
Yeah.
Because I think, if I can push back on that just a moment,
Yes.
I mean, I think the rationale is these complex coefficients, what have they got to do with anything? What we do have is a world that splits into two, so it should be equiprobable.
But the words are different. Well, why should be equal? The words are different. Why should we equal the probability?
Because we can't conceive of what it is to split into two, where you somehow split more in the one case than the other. These complex numbers are just not they're
The
irrelevant
complex,
to anything.
the complex, in the end, complex number are important, but the fact that their words are different, there is no any reason why this should be at the same like this one.
Well, they're not. They're not detectably different.
What?
You can't detect the 0.9 when you're in that world.
Yeah.
But they're different. Here the A is up and B is down. This is enough for me not to put this equal probability. I have no any reason whatsoever to put the 0.
I think the issue is a bit more primitive,
Yes.
it's more sort of elemental.
Yes.
It's that if you split into two, what sense can there be of splitting more into the one than the other?
I don't even want to start with this. I split to two different ones. If I split to two different ones, this different from this one, so everything about this might be different from another one. Why I should put the same number?
Actually, I have the feeling I'm sitting in the wrong universe here. Because how could you believe that the 50% probability is a probable thing, so to say? How could anyone reasonably thinking that 50% should be the right division, so to say, if you divide it into two worlds? The entire world, when you look at it, has different splitting ratios.
What do you think it ought to
But the correct one, of course, the physical one, the 90% and 10%.
I see. Well, okay, I can only, I mean, I'm with
So,
you.
I like that.
I'm with you both, you know, but I'm trying to give the intuition that says, and the reason why many people have said, if the world splits into two, then it should be 50-50.
But if a beam splitter splits,
But they're not thinking like that. It's more...
Well, there could be other people who say, well, the world splits into two, we don't know what it is. How could that 0.9 possibly affect anything if we can't measure it?
There's also that, yeah.
Yeah.
I don't say now that on 0.9 it's important. Even this, even in the end of the day, if the coefficient are equal, I say it's probability equal. But I say that even this is completely not trivial, and there is no a priori reason to put this. The word A is different from one B. One it's passed through, one it's reflected. So if they're different, there is no any. I think only when you have symmetry you can say, oh, they should be equal.
Right, I mean,
Because even in case of 5, you say you have to put 1 5. 1 5, if they 5 equal, so you distribute them equally. But even if they're different, why they should be the same?
I mean, can I just add this? The people who say that, well, it should be 50-50 are people who are hostile to Everett. These are not friendly people. So you understand, I mean, this is their way of being deeply sceptical that there's any meaningful notion of probability at all. At most, there's a notion of, well, maybe you could say 50-50 if the world splits into two. So that's where these people are coming from.
Okay, but so now I'm not in Everett, I'm a collapse. I want to prove a Born rule in a collapse. And because even here, I think it might happen A, might happen B. So why not 50-50? This is, for me, it's similar. I don't think that the fact that there are two of them, that they really exist, I don't see why it gives 0.5, 0.5 more, it's more plausible. I think in the same way they should say there are two possibilities, 50-50. If all this joke about Blonde that she asked if the dinosaur will be on the street tomorrow, what do you think? Either will be or not, 50-50. It seems to me completely... I see no reason, but you somehow see, but it's maybe my problem.
If you're talking about GRW or collapse theory, so then this is a one-world theory, and now there's various reasons why people think this at least is intelligible to me. And fair enough for the physicist to come along and tell me what the objective chances are of these things happening. But it's because it's intelligible already. The trouble with Everett is that there are people who just reject it as unintelligible. And already they'll say this at this point.
So, but now I'm not in Everett, and I'm trying to prove a Born rule without Everett, which is kind of not. If I understand, I don't know if people did it. People kind of usually don't do it. But for me, why I think that many of the proofs in Everett are not of particular importance, because I think the same proof, at least for me, it's more or less the same proof in Everett and not in Everett. So I think I can prove Born rule without Everett.
Okay,
So how it goes? I start with a particle which is completely symmetric, kind of complete symmetry. It's special state, it's wave packets, have 3 wave packets here. I add gedankendly 3 identical persons. They're really identical, sits here, and the kind of, so I have complete symmetry here. And then this person make an experiment and they try to find a particle, and quantum theory tells only one of them will find. And there is a complete symmetry, so this one can find, or maybe this one can find. But I say that in this kind of picture, there is no even meaning for this, because there is no difference between these 2 situations. This situation are identical.
How do you know which one happens then?
Exactly, I don't know. There's no difference. This situation and this situation exactly the same.
But are they different outcomes?
What?
Are they different outcomes or the same outcome?
No, one of them find a particle. So it might be one will find particle or another. This is a particle. I have a particle in 3 places, and then I make a measurement. So this is kind of a wave packet in 3 places.
What does P stand for?
The probability to find a particle, or to find a projection operator on here. Projection to find it here. Projection operator, if it's 1 or 0, if I find or not find. If 1 it's 1, others are zeros. Projection operator to find the particle.
If it's GRW, they have no interest in projection operators. They have no meaning.
The meaning, the operational meaning, if they find a particle or not. What's its
Okay, but don't talk about projection. If it's GRW, if it's a dynamical collapse theory, don't talk about projection operators.
Well, why?
Projection of the Gaussian wave packet.
No, but me here it's really a projection of the whole space. I don't have to specify exact wave function. So what I say in this kind of symmetric, I want to prove something from symmetry, so I start from symmetric universe. But I think I'm stuck here. I cannot continue because in symmetric universe there is no meaning for particular outcome. There is no difference between this outcome and this outcome. I need to put some labels. So I need something which is not symmetric. And I think in physics it's the whole idea, all physics which we do, we say some things are relevant to experiment and some things which are not relevant to experiment. So I'm allowed to break the symmetry by things which are not relevant to experiment. And I assume that these symbols, letters written, whatever, something else, now the observers do not need to be exactly the same. Because it probably, the nature of the observer is a man or woman will not decide if he will have more chance to find a particle or not. So, but now observers are still symmetric, but there are some labels. If there are labels, I can write the quantum state of my particle in this way, ABC, A plus B plus C. And now I can use my symmetry argument. If they all simultaneously in the same moment perform measurement, and according to collapse theory, one of them will find it, I think the symmetry tells me the probability to find the particle is 1/3. The symmetry tells me I don't need to know any quantum mechanics, anything. The only thing which I have to know that things are prepared symmetrically and everything else which is not symmetrical is not relevant to this experiment. So in this case there is 1/3. Quantum formalism shows me the amplitude is 1 over square root of 3, so there is a fitting between the probability and the amplitude square. Now I want to say that this is kind of a general property, and I think without assumption I cannot do anything, because I believe quantum mechanics is physical theory, it's fulfilled special relativity. But collapse is beyond quantum mechanics. It's kind of, I don't know what collapse is, it's kind of a process which doesn't need to fulfill physical properties, but I put the requirement, the collapse fulfills special relativity. I cannot send signals with collapse. And if this is so, then what I say is that I can modify the state in such a way that if so what I'm doing the following. I can perform to move the other wave packets to make one of them, to make interference. So now I moved from one state to another state. In principle, I can do it before the signal about my action go to A. Therefore, results in A should be changed. Otherwise, I would be able to send signals.
So you're assuming that the no signaling theorem applies
for collapse.
and that it can be proved without appealing to probability.
Again?
Well, part of your proof assumes the no signaling theorem.
Yes. So
So
this is
you-
the assumption.
You need a version of quantum theory that obeys the no signaling theorem, and I mean, I don't know whether this is true, whether one can prove the no signaling theorem in quantum mechanics without ever referring to the Born rule.
Is he assuming
No,
the no signaling?
I
He's
assume-
assuming the no signaling principle.
Yes. I
Which is
assume the
different.
principle. Because I think
Is that on top of quantum theory?
yes, on top of
It
it.
depends.
Oh,
collapse.
okay,
Yes.
okay.
Quantum theory is about unitary evolution. Then there is a collapse for which I don't know what it is. I don't know how it works. But then I say I think without some assumption I will never be able to really to get the Born
Okay.
rule. I need something to assume.
Yes.
And what I assume that the collapse will not break my
Yes.
will not break no signal.
Fine.
So, and if it doesn't break no signaling, then therefore the probability to find a particle here for this state and for this state should be the same. So this essentially tells me that the probability only depends on this amplitude, because all this I can change in any way whatsoever without signal coming to A. So the only thing which remains is this thing. So at least for this case, I proved that probability is 1/3. First, I start with symmetry, which I know just by symmetry without any signs. Second, I know that I can use this quantum formalism and change my other things from symmetric case to asymmetric case without sending signals, and therefore I prove this. Now, for this and for this, because it should be the same. I need 1/3, maybe it's not enough. Again, assumption, probability depends on the wave function. This is also kind of, I have to assume this.
Specifically the amplitudes.
No. So it depends on the wave function.
It depends on wave function and the observable being measured.
It only wave function, because before I knew it was symmetric wave function. Now the symmetric wave function can change in any way whatsoever without signal coming to A. Therefore, any modified wave function should have the same probability in A.
But it's the position is being measured specifically.
Yeah, I ask. There is the task is I have this particle in 3 places,
Yes.
and I measure if the particle is in A or not in A.
Yeah.
Okay. But why would not the probability perhaps depend on these A, B's and C's that you introduced?
They were symmetric before,
Yes, I
and
know.
then from symmetry I know that it should be 1/3. Then I know, since I can change B and C to everything to D or whatever I want.
Yes, but that means changing among other. Oh, I see. You don't want that to be the wave function.
So
A, B, C is independent of the wave function. Is that right?
A is
A, B,
wave
C.
packet specified here. I can also have another argument, if I squeeze it, whatever, I also cannot change it. If I even A is a kind of a wave packet here.
Right.
Another argument, why it's not dependent on A.
Yeah, why-
Maybe if
why-
I'll squeeze it, it will be different.
It's got a four-leaf clover in it.
What?
It's got a four-leaf clover in it.
I'm not-
Four-leaf clovers in the Irish folklore, they're lucky. Okay, it's a little leaf,
Ah.
a little vegetable thing. Okay.
Ah.
So it's lucky. So maybe A's got a four-leaf clover in it, and that makes the probability different.
So you,
That is, before I arrange the same fold, whatever, in A, in B, and C.
Yeah.
Therefore, it has to be 1/3.
But you've got,
Now I changed B and C to anything I want.
yes, but these
It's-
are differences to the wave function. A, B,
Yeah.
and C are
You-
differences to the wave function. Maybe
the whole wave function. All you need to do is to change that purple thing to probability depends on the relevant part of the wave function.
I mean, you said this earlier. You
No,
said that
no.
the symbols A, B, and C are meant to be irrelevant actual details. So you sort of outlined this assumption earlier, but now it's not there.
But you're not
Yeah.
really
No,
entitled to
I
the
know,
assumption.
no. A, B, and C is just to kind of, I need some index to
Right.
say that this is.
But those are differences in the wave function.
But earlier you said
No, they're not different. There's a difference in the environment.
Oh, but that's what
That-
A is
That's
environment, not
also
the
in the
wave
wave
function.
function.
What?
Well, the environment is also in the way.
No. Again, there is this question about the density matrix and other system. Here I'm talking about one system, which is one particle, A, B, and C. And I kind of, the idea is that quantum mechanics can tell us what is the probability that I will find this particle. Without mentioning if I bring my dog to space A and not bringing a dog in A. So that some other things in, if it's A, it's Oxford and B is Cambridge, that there is no any preference. It doesn't mean that the building around. What's important that the shape of my particle in A and B is the same.
Maybe it's because the wave function is in the environment A that it thereby determines a different probability.
Okay, so let's start. No, it's very important.
No, but can I just say why I'm making these points? Because if
Yes. You practice, but I thought I was careful. If you remember, I start with complete symmetry. This is complete symmetric situation. Here, absolute symmetry. And then I carefully add this A, and then I add this A, B, C, and I postulate it. There are things which are not relevant to my experiment. So everything which is relevant is completely symmetric.
So that's the point. That should be part of your assumption that there are things that are irrelevant.
Yes.
Because you have just two assumptions. You should have three assumptions.
Sure, without things that there are things which are not relevant, it's important. But I think it's kind of what we...
Irrelevant, or does it help to add the labels later in time? I mean,
What?
Does it help if the three environments aren't labeled initially, but you add the labels later after this wave function has split? Or?
No, I need it from the beginning. Otherwise, I cannot write this A plus B plus C. It doesn't have meaning. I cannot be in a symmetric universe. In symmetric universe, if one find a particle, another find a particle, there is no difference in these two events. It's the same event because there is a symmetry.
But I think it's fine because you said this. It's just that you don't want to elevate this assumption to one of your key assumptions, but it is one of your key assumptions, and I think there's nothing wrong with that.
Well, what's wrong with it is if you assume that the probabilities is a function of the amplitude, you're already home and dry. So you've got to motivate, you've got to demonstrate that the probability must be a function of the amplitude in these cases.
Okay.
And that's what is not...
I didn't assume that probability. First, I assume that it's function of the total wave function.
Right, so it may depend on A. So it's not just the 1 upon root 3, it also may depend on A. What is that one particle state A? So it may depend on that nature of that state as opposed to the one particle state B. Why not?
I start with complete... A priori, I don't know anything about probability.
Just because the wave function has support in the region A, that may make it distinctively different vis-a-vis its probability. It's a lucky bit of configuration space. You're on the origin. I'm lucky. You can't rule these things out.
Look, this is complete symmetry, and here clearly there is no difference if one finds and another finds. There cannot be. There is this indifference. But now I cannot continue. If everything completely symmetric, it doesn't mean that A found or B found. So I need to introduce some. Labels. And then I assume that these labels are not relevant. And this is kind of natural. I don't think that without this I cannot follow.
It is an assumption. You admitted that you need to make the assumption.
Yes.
And Simon, all you're doing is arguing that maybe it's not natural, right? I mean, if you make the assumption, then you can't come back and say A is luckier than B. He's just assuming it isn't.
No, sure, but the issue is what we're trying to do here. I mean, it seems to me the name of the game is to convince the skeptic. Well, the skeptic is going to get off right now and say,
well, there are skeptics and there are skeptics, right?
Well, watch out.
Anyway,
you'll never answer if you're not careful.
May I suggest that we just let Lev finish his argument?
Yeah, but it's a crucial point of view.
Okay, so then there is some. I proved it for 1/3 for 3 cases. Maybe a little more difficult when I have n, because I cannot move all these wave packets to anything I want without signaling coming to A. I again ask. I want to say that probability. Now I have function which is symmetric, which it has 1 over. It's square root of n here, and I want to again ask what's the probability to find the particle here. I want to say it should be 1 over n, and but I cannot immediately to transform this to any kind of state, because if I try to move these wave packets, I cannot move them here, because this distance is smaller, there's some information can come here. But I can move it a little, like here. So, and then I can say the probability in this case, and in this case it should be the same, because all this modification can be done before the signal will come to A. So I know that here the probability is 1 over n by symmetry, and here the probability is 1 over n because it can be modified from here without sending any signal to A. So the probability cannot change here, otherwise I can send signal. Now, if I know that in this situation it's 1 over n, now I can modify it again. I can make another shift so the time cannot from this one to this one. So if I prepare this, I know this is 1 over n because this I can move it from here. So then I know that this one is 1 over n, and now I can know like this one is 1 over n or any other state. So this is really probability and proof that if I have 1 over square root of n as an amplitude, that probability should be 1 over n. Now, from 1 over n, I want to go to any rational number, like m over n. Then I want to say, I can say the sometimes. So I have a rational number here. So I can start with this state. This is kind of this, all of them have 1 over square root of n. I know 1 over square root of n probability 1 over n. Now I know that this should be of m over n because the total probability is 1. So this gives me for square root of m of n for anyone, and I don't think I have, then I can make a general statement because I think it's enough. I don't think that the continuity tells us that rational, irrational, this for all rational, this is good enough. When I make an experiment, I cannot make experiment with the rational number. I can make experiment with, my precision will never be the precision of difference between rational and irrational number. So this is really kind of this general thing. This was for specific special wave function. So we want to say that if I have a spin and I measure in another direction, so I have spin state like this, then probability is 1/3 to get up. So, and this is local. Here, what I use in non-locality of the fact that I cannot send signals faster than light. This state is local. Now, this I think is not this maybe kind of a jump or kind of a step. This is what I want to mean. What does it mean, a quantum measurement? One of the way to make a measurement, if it's up or down, it's to make unitary transformation from this kind of state to this state. I can make a unitary evolution from spin to special degree of freedom. Now this one, I know, for special degree of freedom, I know that it's this kind of state, it's 1/3. So instead of measuring directly spin, I will kind of first split it, essentially, Stern-Gerlach essentially does so. And then, after I split it, then I have the special state. For special state, I know that the Born rule should work, so it should work also for this one. So, it proves then for any, this pure state, if I have amplitude alpha, then probability is alpha squared. Now, going to mixed states, I think it's, again, if I assume I take Landau for granted and the density matrix is complete description, then essentially I have the same proof. If I don't have it, I'm not sure, it's not clear what can I do. So I kind of have to assume that I can use density matrix, but then it can be generalized to a mixed state. Otherwise, it's not clear for me what can I do. So the context. This was in the context of standard quantum mechanics, in which I believe that really I kind of take wave function seriously. For me, standard quantum mechanics, this is what it is. I have wave function, sometimes it's collapsed. it should collapse according to the Born rule, otherwise there is no coexistence with relativity. And the wave function is the whole story. The experience supervene wave function, and many people have see it kind of not problematic, because they say wave function is in 3n dimension, and I think it's important to mention that this collapsed wave function, every macroscopic state, macroscopic body, have a wave function in only 3 dimensions. We have all kind of entanglement, but this is in atoms. Atoms are entangled, but tables are not entangled. The center of mass of table is well localized, so it has a wave function in 3 dimensions. So, and since I interact with tables, I don't interact with electrons in atoms of the table, then essentially my interaction is in 3 dimensions. All macroscopic objects are really not entangled. Experience correspond to macroscopic object. I experience tables, not electron inside the atoms of the table, and therefore I have this picture in 3 dimensions. To live, it's to interact. We live in 3D, so everything for I have a nice picture of everything, and I can accept this kind of story, except collapse. Collapse for me is completely unphysical, so I cannot have this this kind of picture. And but says, okay, there is no collapse. All of them happened. When all of them happened, it doesn't really change experience of any one of them inside any branch. Essentially, every one branch, it's like this collapsed branch. There is no difference. In experience, there is no difference between experiencing in one branch of many worlds or in a world in which there is a collapse to one particular branch. So now the many world is, the ontology is this non-collapsed wave function, and its connection to experience through this kind of each one. The decomposition, what's important, I have to decompose. How I decompose? I can be parasite on this standard quantum mechanics, the collapsed wave function. I think I have to decompose the wave function into the wave function like collapsed wave function according to the textbook. And so the experience is like any textbook. People say that after this collapse, quantum mechanics describe well what we see around. And so there are just many like this. We don't. We have to avoid this problem with collapse, which is not physical. We just say that all of them exist. And alternatively, if I don't want to use standard quantum mechanics, I just postulate these world wave functions are such that every macroscopic object are well localized, and it's really give me the same story. Now I have to put this probability and then put this name, so I use this essentially the same postulate, but they just the same like Born postulate, but now we have this many words, and I think that the postulate about my location in particular world. There is nothing happen. Everything split always deterministically, but it might, when I'm in particular world, I might not know in which world am I, and I postulate that probability to be in particular world is according to the Born rule. If I have no partial knowledge about experiment and I know the results, then I should bet according to the Born rule. Now, so this self-location kind of for me, it's the main things which we need for probability in the many words, because it's not that 0.9 and 0.1. This, of course, there is a problem. Why 0.19 and 1? This is a Born rule which we talk about the proof. But there is no meaning for A and B, because both A and B it happens. So I think the first thing, what is the probability that it will be A and B? When A and B happen together, I don't understand how a priori there is no meaning. I can add an observer and still I know that it is splitting And I still think that in this picture there is no meaning. There is a meaning in collapse theory because there is only one outcome. There is meaning in Bohm theory. It's a statement about where was this initial position. This is a wave function, and if I have this, then every particle which has Bohmian position in this low 10% will end up in B. And so I can ask, but by definition I don't know where I have ignorance. So here I understand. But in many words, I don't think there is a meaning. Everything happened. What's probability? How I can talk about probability? And so I have this trick I can postulate, but what does it mean? And the meaning, so my postulate is that before the experiment I will kind of put bets according to the 0, 9 and 1, because I think I care more for other one. I think the one exists more than others, but these words which philosophers I think really don't like. And my justification that I can arrange situation which will be similar to the cases when we can talk about probability. I believe that we can talk about probability when we have ignorance. In here I can know everything about, if I know everything about my particle and everything about my beam splitter, I still don't know what is the outcome. So here I don't have an ignorance. But how to get an ignorance? I have to perform the experiment. After the experiment, I have to be in a position that I don't know the result of the experiment, but there are two of me after the experiment. How I make two of me? One, I arrange that I will be moved to one place or another place depending on the result of the experiment. So now there are two of me. Maybe if I know the wave function, now I know the wave function of the whole universe, including the wave function of me, that there are two copies of me, one in A and one in B. I know everything, but there is one thing which I might not know, in this case, who am I? And this is a probability which can be defined in many words. This is the only ignorance. The wave, in this, all this quantum experiment, all the relevant knowledge is really given. The only things which is not given, I might not know what is the outcome. So this is how I define this ignorance probability of a descendant of the experimentalist who performs the experiment. And both A and both B, they have the same knowledge, so they put the same numbers. So here they postulate the 0.9, unless there is this proof which I kind of sketched, which I made for collapse theory, which I think the same. Similar proof I can make for many words. So this is the possibility to define it, because as I say, they're ignorant, they don't know what will happen. They know everything what will happen, but they don't know who am I. Okay. It's arranged that room A and room B is similar, so when they wake, they don't know. They know about experiment, they know that there is another copy, but they don't know which copy they are. How I can prove the Born rule in the framework of many words? Exactly the same proof I think doesn't work, because if I look at this experiment, there is no situation of ignorance. I need a situation of ignorance, and to make situation of ignorance, I have to kind of to make this experiment of this type. When I want to test if the particle is here or not here, I really, again, I arrange that I am asleep, and when, depending on if I find particle or not particle, I moved to different situations. Again, I can arrange everything completely symmetric. I can repeat from now on. It's exactly the same story like before, and this gives me a probability of 1/3, and all the rest I can repeat as I did before. Do I see a difference between the many words story or collapse story? In a collapse story, I had to add this no signaling, because the collapse process is out of physics and a priori doesn't have to follow this no signaling. Here I don't need it because quantum mechanics have no signaling built in. Of course, non-relativistic quantum mechanics can signal, but the theory which it might be correct is relativistic quantum mechanics. Relativistic quantum mechanics cannot signal. So clearly, if in this situation the probability is 1/3 because of symmetry, I can change, move object, wave packet, whatever, to any wave what I want until the light signal will come here, and this tells me that this probability shouldn't change. So essentially, I can know that probability of what's happened in A is because of my what's happening in A. Open question when I start to have mixed states, and here usually it's automatically mixed state when it's kind of how to deal with mixed states. Although this kind of mixed state maybe I can deal. Some others, am I allowed to use density matrix? If I allow to use density matrix formalism, then the proof goes. But am I allowed? It's not very clear. It seems to me that I'm not allowed. I will not be able to. I will not able to make rigorous proof, because if I don't, I have to say when I have this system, I have to separate my system from everything else, or my system from other system which is entangled with. How to say that it's property just of this system on others if I don't have any kind of rules? I don't know. Maybe one thing which kind of attack on some other proof, I don't know how important. There is this also kind of symmetry proof with swapping. I didn't have any swapping in my proof. I just said I have symmetrical situation. Because of symmetry, I know that in symmetrical situations probability 1/n. And then since I can modify to any other thing, so it still remain 1/n. The last symmetry proof is swapping, which I understand that this is kind of decision theory also use swapping. At least the seventh proof, seventh kernel, I believe it's flawed, because they say something like this. They consider this kind of situation. There is alias, spin, all kind of detectors, and they say that here, in this kind of state, that there are two aliases. This one alias when the spin is up, and one alias when the spin is down. But this is a quantum state of alias. It's exactly the same quantum state. No difference in quantum state of alias. And they make all kind of swaps, and they're trying to say there are two different. This is one word and this is another word, which I agree, because this is word with detector set so up, detector so down. But from my point of view, there is only one alias, because I can write it like this: there is one alias. If there is one alias, you cannot talk about self-location. Here, if there are two aliases, like in my sleeping pill experiment, I be here or here. I can ask where am I? Also, Tapenin, for example, even then is not ready. There are some ideas that if my quantum state exactly the same, the only difference is position. Some people say it's one me, but for me it's kind of strange metaphysical approach. If I'm in different rooms, even my wave function, relative wave function, is exactly the same. For me, there are two different things.
Where you are is then an irrelevant variable by your criterion.
It's irrelevant because this guy might ask, or this guy may ask. In the end, I can find I'm in room A or room B, and if I bet on A, I will get reward. If I'm not get reward.
If you're a quantum computer and your observer, you said, has to be macroscopic.
Yes.
Is a quantum computer macroscopic if it's an extended object?
The observer is local. This is real problem. This is all observers. I am local, and when we talk about observers, they are local. I don't accept if I have some kind of property, which something's written here, something written here, and the information is written non-locally, this is not all observers in all macroscopic objects and observers are local. So I'm talking about in a word, all macroscopic objects are localized. So I cannot have information in kind of non-local way. So in my world, I have kind of particles in some non-local state with some phase, but it's I in a definite state. So the observers are local. I'm not allowed to. So
I think David was not questioning that. He was
Yeah.
suggesting replace the observer by a quantum computer.
Yes.
So it's a localized quantum computer.
localized quantum and I, what's the difference? There's no difference between a computer.
Right. So
Well, it's just that I don't think it helps to
Well-
move this Alice to two different places,
Well,
because it's just the same thing in a quantum computer.
No, it's not the same. Again, clearly, what are different words? Different words are different stories. Different stories, now the observer can understand because different state of mind, so of course it's different state of mind. But also, if I put the same observer in two places,
Yes.
it's still two observers. Because also kind of classical, if there a copy machine and somebody make a copy of me, how many observers are? The fact that I'm exactly have the same state of mind, exactly the same wave function, but if it's 3 meters apart, so two of me. I can ask if it's this one or other one. There is an operational meaning. Which one it is? I can, in the end, I can say if I'm in room A or room B. There is a meaning. This I. And for this guy, there is no way. There is only one Alice here. So it cannot be asked if the Alice is. There are two words. There is one word in which detectors are up and detectors are down. But these detectors are far away and they are not entangled with Alice. This is a state they consider. So one cannot consider them different and cannot make all kind of swaps on all kind of symmetry argument. I think cannot work like this. So it seems that their symmetry argument, at least in my approach, I couldn't understand how it works. So it's one Alice. This is why I believe one cannot ask question and cannot ask this other question and use this because of swaps, then we get kind of symmetry and get some result. So I stayed with this question. I don't know if some have answers, some has a real question, or some it's. So please let me stop here. It was pretty fast, but at least I can be more careful about the steps of the proof, but I'm not sure. The more kind of the general framework. Do we need them? Is it really a proof? Is it really proof similar to? If I understand that the decision thinks it's like a swap, the symmetry used for swap, which I don't use, so it looks like different. But also, if it's if people really accept that there is a, again, it's not proof from nothing. I have to assume something and then to get a Born rule. But it seems to me that there is not much difference if average is true or collapse is true. I think the Born, at least my proof, most of it is the same. Some think it's even more difficult in many words because I have to define how. I need these sleeping pills and this exercise. Something is better, I don't have to assume no signaling, it's built in. But it's not clear for me which proof is which easier, so I don't know which, if many words has advantage of proving Born rule relative to collapse theory. And I'm not sure that many words can be killed on the fact that it cannot, that Born rule cannot be proved based on many words. Let's postulate, if it gives a nice picture of everything, I think it's good enough.